Good morning, everyone. I'm Wang Yuqiang, an engineer at RT-Thread. Today, I will share the implementation practice of robot real-time control on the vmRT-Thread virtualization platform. More specifically, this sharing focuses on virtualized hybrid deployment for a ROS mapping and navigation robot. Today's presentation is divided into 5 parts. The first part is the background overview. I will explain why embedded systems are moving from a single OS model toward mixed criticality systems, and why the Linux ecosystem and the RTOS real-time control path need to coexist. The second part is a comparison of hybrid deployment options. I will compare RTOS, Linux, hardware-based hybrid deployment, software-based hybrid deployment, and virtualization-based hybrid deployment, and then summarize the advantages and limitations of each solution. The third part introduces vmRT-Thread. I will focus on its key capabilities in resource isolation, virtual machine management, device virtualization, and cross-domain communication. The fourth part is the project architecture of the virtualized hybrid deployment, or ROS robot. I will break down the Linux ROS2 intelligent algorithm domain, the RT-Thread real-time control domain, and the control loop connected by micro-ROS. Finally, I will show the project demos, including the mapping demo, the navigation demo, the final robot system, and the supporting delivery materials. First, let's look at the background. Embedded systems are moving from a single operating system toward mixed criticality systems. Linux has already been widely used in embedded scenarios. Its strengths are very clear: management capability, networking, file systems, graphical interfaces, and a rich software ecosystem. However, in scenarios with high real-time, high reliability, and high safety requirements, Linux alone is not always enough. In these scenarios, a real-time operating system still needs to carry the critical control path. The traditional architecture usually uses two hardware systems. One high-performance processor runs Linux and is responsible for rich functions and high-performance computing tasks. Another MCU, DSP, or real-time processor runs an RTOS and is responsible for real-time control or signal processing. The two systems communicate through I/O, network, or off-chip buses. This architecture can work, but the problems are also obvious. First, the integration level of the hardware is not high. Second, off-chip communication is limited by physical mechanisms such as speed and latency. Third, from the software perspective, Linux and RTOS are relatively separated. This affects flexibility, maintainability, and system evolution. At the same time, hardware capability is changing quickly. Single-core performance continues to improve. Multi-core and heterogeneous multi-core processors are becoming more common. Virtualization technology and trusted execution environments are becoming more mature. Advanced packaging also brings a higher level of integration. These changes provide a solid physical foundation for deploying multiple operating systems on one COC. On the application side, IoT, intelligence, functional safety, and information security are making embedded software more complex. A single OS is facing more and more challenges when carrying all functions. Therefore, mixed criticality systems, or MCS, are becoming an important evolution direction for embedded systems. The value of vmRT-Thread is based on this background. Next, let's look at the requirement trends for hybrid deployment. I think the requirements can be summarized in several aspects. The first aspect is security isolation and monitoring. The system needs to isolate and monitor general-purpose operating systems, such as Linux, and decouple complex application systems from real-time control systems. This prevents an application failure from affecting the stability of the underlying control path. The second aspect is resource sharing. The system needs safe and efficient partitioning and sharing of resources. On the same hardware platform, CPU, memory, interrupts, and peripherals need to be reasonably allocated. Through virtualization-based communication mechanisms, high-efficiency data interaction can also be implemented. The third aspect is the balance between real-time control and AI application deployment. AI and robotic applications are developing rapidly. On one hand, the real-time system is needed to guarantee deterministic execution for motor control and sensor processing. On the other hand, the general-purpose operating system is needed to carry SLAM, navigation, AI algorithms, and rich development tools. Hybrid deployment is used to integrate intelligent capabilities and real-time control capabilities into one system. Now, let's compare several common deployment options. First, RTOS. The biggest feature of an RTOS is hard real-time capability. It can guarantee that tasks are completed within strict timing constraints, so it is very suitable for control scenarios, such as industrial control and automotive electronics. The limitation is that the software and hardware ecosystem is relatively limited. Many complex applications and third-party software packages are not as rich as those in Linux. Second, Linux. The advantage of Linux is its rich ecosystem. Development tools, driver support, network capability, and application resources are very mature. It is suitable for complex functional systems. Linux also provides multi-process isolation and flexible resource management. However, Linux is a soft real-time system, so it may not fully satisfy strict real-time requirements in extreme scenarios. Next are three hybrid deployment methods. The first one is hardware-based hybrid deployment. This method assigns different functions to different hardware. For example, one processor is responsible for complex computing, and another MCU is responsible for real-time control. Its advantage is hard real-time capability and rich ecosystem support. Its limitation is also clear. Resource isolation is at the physical hardware level. Resources cannot be directly shared, and later resource adjustment is difficult because the hardware architecture is already fixed. The second one is software-based hybrid deployment. This method runs multiple operating systems or runtime environments on the same hardware and partitions them through software. It can also provide hard real-time capability and a rich software ecosystem. However, the limitation is that the isolation mechanism between different systems is not strong enough, resource sharing is weak, and later modification or adjustment is still complicated. The third one is virtualization-based hybrid deployment, which is the focus of this sharing. It uses virtualization technology to create multiple independent runtime environments on the same hardware platform. Its advantages are very clear. It can keep hard real-time capability while improving system integration. Resource isolation is based on virtual machine domains, so it is more secure and stable. Resource allocation is more flexible, and the cost of later adjustment is lower. It also supports better resource sharing. Among these hybrid deployment methods, virtualization-based hybrid deployment has the best flexibility and scalability. Next, let's look at vmRT-Thread. This slide shows the overall platform architecture of vmRT-Thread. The system is divided into 5 layers: the application layer, the framework layer, the system layer, the virtualization layer, and the hardware layer. At the bottom is the hardware layer. This layer contains the physical chip and hardware resources, including CPU, memory, interrupts, storage, network, and peripherals. All upper layer systems ultimately rely on this layer for computing capability and hardware access. Above the hardware layer is the virtualization layer, which is the vmRT-Thread virtual machine manager. This layer can be understood as the core scheduling and isolation center of the whole system. It mainly provides 3 capabilities. First, it creates and manages virtual machines. Second, it isolates different virtual machines from each other. Third, it provides communication mechanisms between virtual machines. This virtualization layer is the key to the whole hybrid deployment architecture. It allows one chip to run multiple different operating systems at the same time. Above the virtualization layer are multiple virtual machine runtime environments. This is also the focus of the architecture. The system can be divided into different types of virtual machines, and each virtual machine carries different tasks. The first type is the management VM, also called the privilege of the VM. It usually runs RT-Thread Smart or Linux. It provides management services and peripheral services. Its responsibilities include unified system resource management, peripheral access service, and management and scheduling support for the whole virtualization system. It can be regarded as the control center of the system. The second type is the real-time or safety VM, which is usually a normal VM running RT-Thread or RT-Thread Smart. It provides services through RT-Thread APIs, microROS, or PSX interfaces. Its characteristics are strong real-time capability, low latency control, and suitability for safety-critical or control-oriented tasks. Core control logic in industrial control or automotive electronics is usually placed in this type of VM. The third type is the rich application VM, such as Linux or Android. This type of virtual machine carries complex computing capabilities or user-facing interactive applications. In our project, the ROS2 and DDS robot applications run in this domain. Android HMI, GUI, multimedia applications, AutoSAR adaptive platform applications, and AI computing tasks can also run in this type of VM. In summary, vmRT-Thread is an embedded virtualization platform for hybrid deployment. It uses one virtual machine manager plus multiple heterogeneous operating system VMs to organize real-time control systems, general computing systems, and human-machine interaction systems on one chip. Now let's look at vmRT-Thread's resource management and device virtualization capabilities. To run Linux and RT-Thread at the same time, the platform needs to handle CPU partitioning, memory mapping, interrupt injection, system service, para-virtualization, display and storage access, network channels, and peripheral adaptation. For CPU, vmRT-Thread supports ARM-v8 extensions and 64-bit CPU partitioning. For memory, it supports static mapping, partitioning, and sharing. For interrupts, it supports tick mapping, partitioning, and sharing. For system services, it supports para-virtualization mechanisms such as PSCI and SCMI, including power domain, frequency, and voltage scaling, and pin configuration. For display and graphics, it supports pass-through, shared display, Virtuo GPU, and vendor-specific display virtualization solutions. For storage, it supports pass-through or Virtuo BLK backend. The backend can be based on files or partitions. For networking, VirtuoNet can be used as a virtual switch or router, and IVishMemeth can be used for direct network communication between virtual machines. For other peripherals, such as SPI, IIC, and CAN, the platform can be adapted according to customer requirements. So far, we have discussed the background of hybrid deployment, compared several deployment options, and introduced the platform capabilities of vmRT-Thread. Next, let's focus on the virtualized hybrid deployment ROS robot project. The main control platform of this project is RK3588 or RockPi 5B. It has an 8-core CPU architecture, including 4 Cortex-A76 cores and 4 Cortex-A55 cores, and the platform has 32 GB RAM. It is suitable for single-set multi-system deployment. From the bottom up, the hardware layer provides the resource pool, including CPU, memory, I/O, communication resources, storage resources, and robot peripherals such as LiDAR, IMU, motors, encoders, USAT, and USB. Above that is the vmRT-Thread virtualization layer, also called the Virtual Machine Manager. It provides multiple system runtime environments upward and manages SESE resources downward, including CPU, memory, interrupts, storage, network, and peripherals. It is responsible for isolation, allocation, device virtualization, pass-through, and inter-VM communication. At the upper layer, the project is divided into 2 system domains. The first is the Linux ROS2 domain. This domain focuses on non-real-time, high-performance computing and the robot algorithm ecosystem. It preserves the ROS ecosystem and is responsible for perception, mapping, navigation, localization, and human-machine interaction. The main modules include SLAM mapping with SLAM_G mapping, navigation with nav2, localization and map handling with the MCL and COSMAP, and visualization with RVIZ or GUI. The second is the RT-Thread real-time control domain. This domain focuses on deterministic execution, chassis control, and peripheral feedback. It carries the real-time control path of the robot. The main modules include motor control, chassis kinematics, micro-ROS, micro-XRC DDS, PID, PWM, encoder reading, GPIO, and USTD. The Linux ROS2 domain and the RT-Thread domain communicate through inter-VM communication and micro-ROS. Typical data includes CMD_VEL, ODM, status, and feedback. Linux keeps the algorithm ecosystem, while RT-Thread carries the real-time execution path. Now let's make the value of this virtualized hybrid OROS robot more concrete. The first value is the virtualization foundation. vmRT-Thread provides resource isolation, system boot, peripheral sharing, and cross-domain communication. It organizes the Linux ROS2 domain and the RT-Thread domain on the same SoC. The second value is the intelligent application domain. The OROS robot system is responsible for sensor access, SLAM mapping, nav2 navigation, and RVIZ visualization. It keeps the OROS ecosystem and reduces the development and validation costs of robot algorithms. The third value is the real-time control domain. The RT-Thread platform provides real-time scheduling, device drivers, chassis control, motor execution, and encoder feedback. It carries the low-level control path of the robot and improves determinism and reliability. The fourth value is higher integration. The traditional Linux plus MCU dual hardware solution converges onto a single RK3588 controller. This reduces hardware links, wiring, and external communication dependencies. From the product perspective, the project can be summarized as 1 controller, 2 system domains, and 1 control link. The same RK3588 controller runs perception, decision-making, and execution end-to-end. In other words, 1 controller board carries both the intelligent algorithm domain and the real-time control domain, forming a deliverable, reusable, and scalable robot control platform. Next, let's look at the function split between Linux and RT-Thread. On the Linux OS2 side, Linux is responsible for perception and decision-making. It performs algorithm computing, sensor access, mapping, localization, navigation planning, and visualization debugging. The chain starts from sensor access. LiDAR and IMU data enter ROS2 as laser scan and other sensor messages. Then SLAM mapping and localization are performed, including SLAM mapping, AMCL, and COSMAP. After that, NAV2 performs path planning and outputs CMD_VEL. RViz and NoMachine provide visualization and interaction. Between Linux and RT-Thread, MicroROS connects the two domains. The Linux side runs the MicroROS agent, and the RT-Thread side runs the MicroROS client. Communication can be based on TCP, UDP, UART, or virtualized communication channels. The downlink mainly carries CMD_VEL, and the uplink carries ODEM, status, and feedback. On the RT-Thread RTOSS ID, RT-Thread is responsible for real-time control and execution. The control task receives CMD_VEL and runs the chassis control thread. The control algorithm performs PID control and PWM output. The chassis execution layer drives motors through GPIO and USTD. The status feedback layer reads encoders and reports ODEM and status back to the Linux side. At the bottom, vmRT-Thread provides system domain isolation, resource allocation, peripheral virtualization, and communication support. This is the foundation that allows the Linux algorithm chain and the RTOS real-time chain to run together on one hardware platform. The next part is the product documentation package. The delivery package is relatively complete. It includes software images, SDK and source code, deployment guides, developer materials, tuning and performance documents, and vmRT tutorials. For software images, it includes the Rockpi 5B Ubuntu image and the Ubuntu desktop VM image. It also includes the VMware workstation environment and NoMachine clients. For SDK and source code, it includes the ROS workspace, the MicroROS agent workspace, RTT head source, Hyper SDK, and driver or device support. For deployment documents, it includes the vmRT-Thread overview, the Rockpi 5B deployment manual, ROS2 migration materials, NoMachine usage, and the integrated VM development platform. For developer materials, it includes the project guide, experiment manual, ROS2, SLAM and NAV2 source walkthrough, obstacle avoidance analysis, and driver analysis. For tuning and testing, it includes the system test guide, NAV2 parameter tuning, configuration specifications, and runtime validation materials. This package is designed not only for a demo, but also for delivery and reuse. It reduces integration uncertainty by pairing runnable images with source code, deployment manuals, and tuning documents. Finally, let's look at the demos. The first demo is the mapping demo. In this demo, the robot uses LiDAR data and ROS2 to build a 2D SLAM map. The laser scan data enters ROS2. The SLAM algorithm continuously updates the map and robot pose. RViz visualizes the map building process. During the demo, the operator can use keyboard teleoperation to control the robot and scan the environment. The second demo is the navigation demo. Navigation is based on the map generated in the previous step. First, the saved map is loaded, such as my_map.yaml. Then the operator sets a 2D goal pose in RVZ. NAV2 generates motion commands and plans the path. The commands are sent through MicroROS to RT-Thread, and RT-Thread performs chassis execution. During the movement, the system continuously uses feedback information, such as ODEM and status, to support navigation and control. Through the mapping demo and the navigation demo, we can see that the whole system has formed a closed loop. ROS2 handles perception, mapping, and planning. RT-Thread handles real-time execution. And vmRT-Thread provides the virtualization foundation for isolation, communication, and resource management. That's all for today's sharing. Thank you.